All right, everybody. Happy Monday to you and welcome back. You survived an exam over the weekend or over the last few days, so congratulations. Couple of things. There are a few people that haven't taken the exam yet because of various emergency situations. So I won't post the key for another couple of days, but I'll make a video as we've done previously where I go through and explain each of the questions, and you're welcome to come talk to me about your exam. In fact, I encourage it. My office hours are right after this class, Monday, Wednesday, and Friday. Other times, you can email me to suggest a few times, and I'll pick one. Let's see. The median score, I'll also enable today for those of you who have taken the exam to see your items missed and what your responses were. Let's see, the median score on this exam was 78%. So that's a little bit lower than the first exam. That is exactly what should be going on here, at least in terms of historical trends. The material is increasing in complexity, and so I'm very pleased with that. You guys are doing great. If you got a score that you like, congratulations. If you got a score that you didn't like, first, let's talk because it might not be as bad as you think. And then we need to figure out how to change your study process to better enable you to detect ahead of time what's going to be difficult for you on the exam. Let's see. Is that all? Any questions you want to ask? Okay. Well, back to it then. Last week, we were talking about reaction mechanisms, and in particular, we had focused in on substitution and elimination reactions. We had originally envisioned two reasonable substitution reactions, this Sn1 reaction where Sn2 reaction where a nucleophile attacks the LUMO at the carbon, that's the carbon iodide sigma star. You make a new carbon-nitrogen bond and you break the carbon iodide bond. Importantly, this comes with inversion of stereochemical configuration, meaning that the nucleophile comes in from the backside of where the carbon iodide bond is. But I also told you, though this is a chapter 8 thing, we're doing both of them at the same time because I want you to see the complexity from the beginning. Because of sigma to sigma star hyperconjugation, some of the LUMO is actually out on these beta protons, which means that a nucleophile that approaches the molecule has to choose, am I going to attack carbon or the hydrogen? And if you attack the beta hydrogen, three things then happen. First, the hydrogen gets removed. That's just a standard deprotonation reaction. As it's removed, the electrons in the carbon-hydrogen bond kick over to form a new pi bond between carbon, and then iodide leaves. If you want to think of this in terms of orbitals, okay, nucleophile removes proton, then electrons left behind dump themselves into the sigma star, making a new pi bond, and iodide leaves. One of the things we talked about is that there, in some cases, are multiple kinds of beta protons. Yeah?
Just curious, so if you said the LUMO is due to hyperconjugation sometimes over on the hydrogen side.
Yeah.
So why does the hydrogen leave if it's still attacking the LUMO?
Why does the hydrogen get removed? If it's attacking an empty orbital? That's a good question, and I think probably the way I've framed this is maybe oversimplified, but I don't really understand it at a deeper level. If you want, if it's easier, you could just remember that hyperconjugation makes the beta proton somewhat acidic. And therefore, if they are removed, the electrons in them can dump fully into the sigma star, and that breaks the bond, makes a new pi bond, and the leaving group leaves. So it may be easier to think about it that way.
Okay, so the electrons in the hydrogen carbon bond move into the sigma star.
Right, move into a sigma star to make a new pi bond, and the leaving group leaves. And yeah. Okay, anything else there? So elimination is a little bit more complicated. We have a bond breaking, a new bond forming, and another bond breaking, all in the same concerted step. Let's see, we noticed that there were cases where there were multiple kinds of beta protons, and in such cases, though we'll talk about, there will be times when only one of multiple possible beta protons is reactive. In this case, you could get either the cis or the trans isomer, and you could also get this other, these are stereoisomers, you could get this other constitutional, or we might say regioisomer, where the connectivity is different, where the pi bond is over here with the less substituted carbon, and you would get that by removing this beta proton. We will learn how to predict which is the major product. For now, it's enough to recognize that you could get multiple things. All right, those were concerted reactions. Then we talked about an alternative for substitution wherein the leaving group would leave first, and that was kind of difficult to imagine, but we thought about the leaving group as being bonded to the carbon as being on a spring, and if enough kinetic energy gets transferred to the molecule in terms of vibrational energy, then we can actually get outside this barrier and separate the iodide from the carbocation. That's an uphill step because it involves bond breaking, and because it's a low probability occurrence. But once we make the carbocation, then the nucleophile can come in and attack the carbon. You go through another transition state that simply involves the nucleophile approaching the carbon, making the new bond. And because this transition state involves bond making, whereas this one involves bond breaking, the first transition state's higher in energy than the second, which makes this first step our rate determining step. And we talked about how, therefore, at the very end of last time, we talked about how the relationship between the transition state and the intermediate. That's something called the Hammond Postulate. I'm never going to ask you true or false. The Hammond Postulate says this, because memorized questions are not really... memorized questions are generally beneath you, right? So what does that process mean? Well, what does that postulate mean? It simply means that if two adjacent states on an energy diagram are close in energy, they must be close in geometry. So we're going to make a connection between the structure of the transition state and the structure of the intermediate, which is crucial because we can observe and do experiments on intermediates. We can't observe and do experiments on transition states. They don't last long enough. And so if we know some things about the stability of the carbocationic intermediate, then we know some things about the height of the transition state, and therefore we know some things about the rate of the reaction. Okay, so Hammond Postulate says structure of carbocation is related to structure of transition state. Therefore, carbocation stability is related to transition state stability, which is related to rate of reaction. So we talked about carbocations last time, and I showed them in order of increasing substitution: methyl, primary, secondary, tertiary carbocations. All are trigonal planar, sp2 hybridized with an empty p orbital on the carbon that's positively charged. And they shown here in increasing substitution, they are also in that order for stability. That is, the tertiary carbocation is more stable than the primary or the methyl carbocation. Now, these are all reactive intermediates, so I don't want you to come away with the idea that tertiary carbocations are the kinds of things you can go buy at the store and they'll be shelf stable indefinitely. No, they're very, very reactive, very unstable. It's just that this is less very unstable than this tertiary one is less very unstable than the secondary one, and that's why I sort of wrote that pattern there. Now, you can memorize, and it's fairly simple to memorize, more substituted carbocations are more stable. But it's better to know why. We talked about how sp3 carbons are less electronegative than sp2 carbons. So the more sp3 carbons you have around that carbocation bonded to the carbon that's positively charged, the more of an inductive electron donation effect you can get. This is the opposite of inductive electron withdrawal, where we saw in acid-base chemistry having nearby electronegative groups could stabilize a negative charge. Here we're talking about stabilizing a positive charge by electron donation because of less electronegative groups that surround the carbocation. The second explanation is hyperconjugation. You have, for every alkyl group you have adjacent to the carbocation, you have carbon-hydrogen bonds that can donate electron density into the positive charge and stabilize it, spreading it out. Now, one consequence of this is that some of the LUMO is also out on those hydrogens. So we're going to see a similar competition here. When a nucleophile gets to this stage, it's going to either attack the carbon, and if it attacks the carbon, you can get a substitution product. Of course, the p orbital is evenly distributed on either side, so we have to account for attack from both above and below. So in the case of our, in the case of our secondary alkyl halide, and I'm just going to show you the Sn1 mechanism. Once we get to the planar carbocationic intermediate, we lose chirality, and the nucleophile can come in from above or below, and so you get a 1-to-1 mixture of the two stereoisomers. All right, and this is the first thing we're seeing in terms of distinction between Sn2 products versus Sn1 products. Recall that for the Sn2 reaction, the attack happens in a concerted fashion from the backside, and so we get inversion of stereochemical configuration. And so we would only see for the Sn2 reaction this product, where the nucleophile came in from below. That's really important. It's really important for you to realize, because if for the Sn2 reaction you draw both of these stereoisomers, you are communicating that you think you get both backside and frontside attack in an Sn2 reaction, or you're communicating that you think the Sn2 reaction has a planar carbocationic intermediate. And those are both wrong. Okay, so what you show for products demonstrates how well you understand the mechanism. In contrast, if for the Sn1 reaction you show just one of those stereoisomers, you are communicating that you think the Sn1 reaction either has the nucleophile favor just one side of that empty p orbital, or that you think that the Sn1 reaction is concerted backside attack with inversion of configuration. And that's also, both of those ideas are wrong. So you're going to show your understanding of the mechanism. Even if I don't ask you to draw the mechanism, you're going to show your understanding of the mechanism by the products that you draw. So this is a nice way to demonstrate what I've sort of been trying to tell you from the beginning, that you can try to memorize what happens, as in, okay, an Sn1 reaction gives me these two products, an Sn2 reaction gives me this product. If you understand mechanism, then the products just sort of fall out automatically from the mechanism. The mechanism derives the products for you. But sometimes mechanism can be difficult to remember or memorize. If you understand why things are occurring in terms of the orbital picture, then you can remember, then it becomes easy to understand why the nucleophile could attack from above or below on this carbocationic intermediate. All right. I guess the other thing I would say at this point is that if you have some of the LUMO on the nearby hydrogen, we can call it a beta hydrogen, then the nucleophile, instead of attacking the carbon, could also attack the nearby hydrogen. You might expect above, when the sigma carbon hydrogen sigma bonding orbital was hyperconjugating into the sigma star, I told you that made the beta proton more acidic. That's an even bigger effect because now you've got, instead of a higher energy sigma star, you've got a very low energy MTP orbital. Hyperconjugation is way more significant here, which makes this proton even less electron rich. Imagine the electrons in this carbon-hydrogen bond partially donating into the positively charged carbon with the MTP orbital. The more these electrons are delocalized, the less tightly the proton is held. And so it doesn't actually take a very strong base at all for us to remove that proton. And as we do, the electrons in the carbon-hydrogen bond dump fully into the MTP orbital to create a new pi bond. And so we're going to see, as we did before, elimination products. So I think for this particular example, this is an elimination product. So we're going to call this an E1 reaction. You'd be tempted to think of it as something entirely different from the Sn1 reaction, but they have the same first step. So they are sort of the same reaction. And in fact, for our purposes, we're going to see that Sn1 and E1 always compete with each other. So we're going to see that if we think a reaction mechanism is going to be Sn1, we're also going to show E1 products. And I'll give you some specific examples of that later on. So now we've got 4 mechanisms, the Sn2 and the E2, that compete with each other, and we have the Sn1 and the E1 that compete with each other. And now we need to explore what changes the free energy landscape of our reaction to favor one mechanism or one outcome versus the other. So what I want to do now is attempt to draw a 3-dimensional free reaction coordinate energy diagram. It's going to be terrible, but I think if you have a good imagination, it may be good enough. But before we go there, any questions about these basic reaction mechanisms? Yeah.
Sorry, could you just explain one more time the difference, what an E2 reaction looks like?
Sure. The E2 reaction is different from the E1 reaction in the sense that in the E2 reaction, we remove the proton, pi bond forms, and the leaving group leaves. Whereas in the E1 reaction, the leaving group leaves first. We get a carbocation, then we remove the beta proton and make the pi bond. Yep. Others? Okay, so to set this up, I've got a drawing here in my notes of what I did last time, and it's pretty terrible, but actually I'm kind of proud of it in a weird way. So let me try to set this up. We'll start out 2-dimensional, and we'll start out not even thinking about energy yet, okay? Remember in the Sn2 reaction, remember in the substitution reaction, there are 2 things that can happen. You have the leaving group leaves, and you have the nucleophile forms a new bond. So leaving group leaves, we're going to break the carbon, whatever the leaving group is, bond. the sigma bond. And then we're going to make...
Which reaction are we talking about?
We're talking about all of the substitution reactions. Involve these two steps in some order. For breaking a bond between carbon and leaving group, making the new carbon nucleophile sigma bond. So, really, we've got two different ways to measure reaction progress. We might say that on this axis, we have breaking of carbon leaving group bond. And we'll imagine here is 0 and here is like 100%. So as I start out over here, the leaving group hasn't left at all. By the time I get here, it's completely gone. Okay. Similarly, on the y-axis, I'm going to put, if I stand sideways, I can do this, forming of the carbon nucleophile sigma bond. So, and we go from 0 to 100%. So if I go exclusively down this pathway, is this what we wanted? Sure. Do you mind if I change axes? Yes? I'm very sorry. Okay, let's do forming the carbon nucleophile sigma bond. It'll be better this way, otherwise our drawing was going to look more terrible than it is. Break the carbon leaving group sigma bond. Okay, so to review, on the x-axis, we are, as we go from left to right, we are forming the new carbon nucleophile bond, and as we go from top to bottom, we are breaking the carbon leaving group bond. All right, so now I just want to, and we're not even talking about energy yet. Energy is going to be the z-axis coming out of the page at us. So let's, I want to trace out the two possible substitution pathways we have looked at so far. The first is going to be the Sn2 pathway. This is concerted forming and bond breaking at the same time. And then the second is going to be the Sn1 pathway, where we break the carbon leaving group bond first, and then we make the carbon nucleophile bond. And maybe I'll just complete the square. Ooh, that's a thing from math, I think. All right, so what's the sort of mapping out our trajectory here, or what happens in the reaction? What's my pathway for the Sn1 reaction? What do I do first? So I'm going to go straight down along this pathway here. And that means this corner of the pathway represents my carbocationic intermediate. And if we want to, we can draw our alkyl halide here. And as we get all the way to the bottom, then we get to our planar carbocationic intermediate, and also the leaving group has left and is gone to sort of infinite distance. So I'm going to put it way over there. Okay, and then what for the Sn1 reaction? Then what happens at that stage? Then your nucleophile comes in, and right here, this corner then is products, And this is where we would get, and I'm not going to say there are different stereochemical consequences for the Sn1 pathway versus the Sn2 pathway, and we're not going to account for that very much, at least in this energy diagram. But you'll have to remember, and the reason I've drawn I'll put in parentheses here, this is the Sn1 product. The reason I've drawn this stereocenter without dashes or wedges is because I'm communicating with that line that I actually have both configurations. That's one of the ways you can communicate that. All right, so then the Sn2 pathway is what?
Just go straight.
We're going to sort of go diagonal. The leaving group leaves as the nucleophile's coming in. Okay? And actually, you see that if you can imagine this pink line as a string stretched between 2 points, we might be able to grab a hold here and pull it this way, and maybe we'd get a reaction where, a version of this reaction where the leaving group started to leave more first, and then the nucleophile came in. And that's something we talk about in my advanced OChem course. You don't need to worry about it, but just realize that there is a continuum between Sn2 and Sn1 in which we could vary the extent of leaving group leavingness versus the nucleophile coming in. So I don't want you to think about Sn1 and Sn2 as sort of discrete options where it's either one or the other. In some cases, there's a continuum between them, and that's okay. For our purposes, you can think of them as two of the possible options, but just realize there's a lot of landscape in between here for reactions to proceed. All right, any questions you want to ask here? Yeah, go ahead. Oh, thank you. Sorry.
And so that's also not going the opposite direction as the original iodine. It's just going straight with the pitch, not interhouse.
Right. Yeah. So if this were indeed an Sn2 reaction, Sn1 reaction, I'll show you actually 3 ways.
That's what you were saying is like that's the combination of.
Yes.
Okay.
Yeah. I'll show you 3 ways to draw both enantiomers. You can either do it like this. You can do it like this, though if you do this, you have to be careful if there's other stereocenters in the molecule. You can also draw just one of the 2 enantiomers and then put a little plus minus in parentheses by it. That's a reference to optical rotation. The plus minus symbol means you've got a 1-to-1 mixture of enantiomers. So either of those options is okay. All right, other questions? All right. Let's talk about transition states, because we're not showing energy yet. That's on the z-axis. But my starting materials are here. My products are here, so where would I put the transition state for the Sn2 reaction? Yeah, it's going to be somewhere, and it's difficult to say, and exactly where along this line it falls is not important. Just that the transition state represents us being some way along this pathway where the leaving group has left a little and the nucleophile is coming in. So, you can put it at 50% and that's fine. It doesn't have to be that way. It just happens, whatever is the highest energy configuration along this pathway. So I'm going to hedge and just sort of put it there. This is the Sn2 transition state. Okay. How about the transition state for Sn1? Where am I going to put that?
Would it be 2 along both, like somewhere in?
Right, because I'm going to need 2 of them because I have an intermediate here. That's an energy minimum, so I'm going to have 1, and I'm not exactly sure where to put it. I'll just guess. We'll call that the Sn1 transition state A, and then you've got another Sn1 transition state B. Now, actually, I take it back in terms of where to put that Sn1 transition state, because we've said that because the Sn1 transition state is close in energy to the intermediate, they have to resemble each other in geometry. So we're going to reflect that. We're going to put the transition state somewhat late along this trajectory to indicate that this transition state is going to be very much like a carbocation. And if you were to go on and study organic chemistry, people would use the Hammond Postulate to talk about early versus late transition states, and this is exactly the kind of thing that they're talking about. All we mean is that because they are close in energy, the Sn1 transition state A looks very much like a carbocation. Not completely, but pretty close. All right, so those are our two pathways for Sn1 and Sn2. Go ahead.
Does transition state B not matter where it is on the horizontal line? Or should that also be close to the intermediate?
So yeah, question is, does transition state B matter where it is on the horizontal line? Not for reaction outcomes, because that's not the rate determining step, but you would predict transition state B to be early in the sense that it is also close in energy to the intermediate.
Okay, that's what I thought.
Yeah. Okay. Other questions? All right. Shall we make it worse before we make it better? Yeah. Yes. Before we even go on to making this three-dimensional, it's painful because I've already moved some stuff around. Okay, well, that's fine. We're going to take our drawing, and I may need to move some stuff to make room for what we're going to draw, or at least shrink some stuff. So I don't know. I think we can get rid of the iodide. I don't know. I don't really know what to do with this little note other than dotted line. Okay. So the reason I erased that is because with the leaving group leaving, we need to think about the other possibility, which is elimination. Right? So remember that elimination reactions also involve leaving group leaving, whether that's an E2 type reaction where the leaving group leaves at the same time as you remove the proton, or the leaving group leaves and then you remove the proton for the E1 reaction. So I'm going to draw another direction. And along this direction is going to be, I have to try to make sure it's the 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. And I lost count already. I should have, that was dumb. My apologies. So along this axis, we're going to put removing the beta proton / forming pi bond. Okay, and we're going to keep this axis of break the carbon leaving group bond because that is something that the elimination reactions have in common. All right, so down here at the corner, we're going to have elimination products. And for this reaction, I'm just going to draw what we drew above. You've got the trans, you've got the cis isomer, and you've got the regioisomer. Okay, so the E1 reaction is going to follow the same pathway in the first step as the Sn1 reaction is, that is, leaving group leaves. And it's only when you get to that carbocation that you have a branch point where you could choose to go this way and get the substitution product, or you could choose to go, let's say, to the left. We'll call this the E1 transition state, and that would give you the elimination products. And what we're saying when we say that substitution and elimination products, that Sn1 and E1 always compete, is that there's not a big enough difference in the energies of the Sn1 transition state B and the E1 transition state to make it easier to go one versus the other. You're going to go both directions. Okay. Imagine a waterfall where you've got two different pathways you can take, and they're roughly the same size and energy, so you go over both. Roughly the same height, so you go over both. How about the E2 pathway, where we remove the proton at the same time as the leaving group is leaving? Just going to be one of those diagonals again, right? But this time going this direction, and there will be some E2 transition state. Now, I told you that Sn1 and E1 always compete because they're not that different in energy, and so once you get to the carbocation, going this way versus that way is about the same speed. In contrast, we're going to see the Sn2 transition state and the E2 transition state. Sometimes they're close in energy, other times are quite far apart. So we will see times where we get both Sn2 and E2 products, but we'll also see times where we get all Sn2 and other times where we get all E2. Okay, so this is sort of laying out the whole picture, the whole competition. And we're going to determine what happens based on the stability of the carbocationic intermediate. We're going to determine what happens based on the structure of the starting alkyl halide. We're going to determine what happens based on the structure or the identity of the nucleophile / base that does the removing of the proton. Okay? All right, do we need to, at this stage, visualize the three-dimensional landscape with energy, or can you imagine that? I don't know. What the heck, right? Okay. I warned you. All right, we're going to do our best here, and it's going to be pretty. This is our challenge for, didn't know when you took OChem that it was basically going to be a drawing class. I went to a wedding over the weekend, or a wedding reception of the kids or a daughter of one of Amber's grad school friends. We're now old enough that our friends' kids are getting married, which is kind of weird. Like, we don't know the kids, but we know the friends, so we go to their wedding, and then those of you that are fairly newly married know how it is. Your parents say, "Oh, this is so and so." You're like, "Great," and then you move on. Well, it turns out the bride was a former student of mine. She had taken my 351 class, or maybe it was 352 at the same time that Amber was starting grad school. And so there was no recognition at first, but then she realized who I was. But in the wedding book, I drew a little reaction, and I also drew my famous 7-membered ring. You don't see these yet, but students are generally impressed by how fast I draw 7-membered rings. They're also impressed at how they sort of look like sad robots. So I drew her this picture. I didn't say it was a sad robot, but I'm sure that will be very meaningful to the family over the years as they reflect back on their wedding day. Okay, so let's start. Here is going to be sort of our starting materials point. Here is the going over to, here is the forming the carbon nucleophile sigma bond. Then along this axis, we're going to do breaking of the carbon leaving group sigma bond. And then going the other direction, we're going to have removing the beta proton. We'll just call it that, / form the pi bond. Okay, and then, oh, somebody thought I was saying something to their device. Does my computer, okay Siri? No? It was somebody, oh, it must have been Google. That's, you don't say okay Siri, you say hi Siri or hey Siri, but for the Google you say okay Google or something. I don't even know. Frankly, I think it's creepy, but and Siri doesn't understand me very well, so it's not worth the trouble. So along the z-axis, we have, oops, sneeze, excuse me, energy. Okay, is that good enough? Maybe. I'm gonna need to move this down just a little bit. Okay, so the Sn2 pathway, and let's just put our starting materials. I don't like the energy there. I'm just going to put it up at the top, get it out of the way. Let's put our starting materials somewhere here. So this is the starting materials in our reaction. And we'll orient where we're going with these other lines. This is 0, this is 100%, this is 100%, and this is 100%. All right, so I'm going to draw along the bottom the lines that we drew in our drawing here. So this is the Sn2 pathway. This is the Sn1 pathway. This is the E2 pathway. And then I think I used this blue for the E1 pathway. All right. Okay, so let's start with the starting material. This is a very good place to start. I think I want to move it down just a little bit. And I'm going to sort of follow this diagonal trajectory, and this is where the drawing in 3 dimensions is. And is going to not look that great, but you have to imagine. So we're going to go up a hill and get to the transition state, and then we'll go down the hill to get to products. And so, though I haven't drawn it particularly well, you need to imagine that along each of these points, I'm moving along this line at the bottom, and here is the Sn2 transition state. Yeah?
The Sn for the starting material, did you sort of put it that high just because, like, not for any reason, or is it?
Yeah, it's just wherever we start. Generally, if these reactions are thermodynamically favorable, the products are going to be more stable than the starting materials, or we'll have to do something to push the reaction that way. Okay.
Saying the energy goes negative because it's exothermic?
It's downhill. The delta G or H for the reaction is downhill. Yeah, it would be exothermic.
Okay, delta.
Yep. Okay. You know, that pink curve is bothering me a little bit because it looks like it's sort of sloppy and leaning to the side, but I think that's the best we can do with the time allotted to us. Okay, so then the Sn1 pathway, and we said that the transition state for the Sn1 pathway is relatively late. And we also said that the transition state energy is pretty high. Carbocationic intermediate is pretty high. So I'm going to say we're going to end up, of course, a straight line. I'm going to just draw straight dotted lines to guide our eyes so that we know roughly where the energy of the starting material would be. Needs to be parallel to the other one. This is fun, isn't it? Okay, so this would be sort of the relative energy of your starting material. Let's put, yeah, the carbocationic intermediate up top. And then here, even higher up, would be transition state A for the Sn1 reaction. Okay, so now we just have to draw a curve where we go up here and then down there, which now also looks like it's leaning towards the other side. That didn't help, that made it worse. Okay, and maybe we'll color it in with shading. All right, so that's the carbocationic intermediate. Then where am I going to go? Remember that the transition state 2, the one where the nucleophile starts coming in, transition state B for the Sn1, is also right about here, but it's not quite as high in energy as transition state A. And you have to view this point as being aligned with this portion of the x-axis. So we're going to go up from here again and then down to this point. And this has to be in front. Okay? We losing it? Are we sort of okay? Right. Maybe. Okay, well, yeah. So see that going through the Sn1 reaction is this way, going through, Sn2 is this way, going through the Sn1 reaction is this way. And see that the competition between those two is going to depend on the relative heights of these transition states. Is it faster to go Sn2 or is it faster to go Sn1? We're going to see a very similar thing over on our left-hand side of the picture in purple. We could draw, let's just put the E2 transition state here, dotted line. We'll put that roughly the same height as the Sn2 transition state. So I'm going to go, oh, that's just terrible. And that's not a very smooth curve, but, you know. So this is the E2 transition state. So now you can see there's also a competition between Sn2 and E2, which is going to depend on the relative heights of these two barriers. And then finally, you've got the E1 transition state, which occurs right about here. We'll put a dotted line up there, and we're going to see it's basically the same, oh man. It's basically the same height as the transition state barrier for the Sn1 reaction. So we'll call this the E1 transition state. We go from here to here and then down the hill there with yikes. Well, so what we've attempted to draw is a multi-dimensional free energy landscape. The point is, what's the point? I'm going to see if I can save it with shading as we talk through it. Nope, need a bigger, there we go. The point of all of this is that I want you to understand from the beginning, even before we get into a lot of details about reactions, I want you to understand that the complexity we're seeing here is just because, well, or rather that the substitution reactions exist in competition with the elimination reactions. And I want to use this as a framework for understanding why one thing happens versus something else. Sorry, I'm like totally distracted by the coloring. I don't know if that helps. Anyway, so we're going to talk about things that favor the Sn2 reaction over the Sn1 reaction and over the E2 reaction. We're not going to talk about things that favor the E1 reaction over the Sn1 reaction because these transition states will be similar in height. Okay, so with that in mind, let's pause from that somewhat hellish experience, and we'll be back at the top of the hour.